Hi, everybody. Welcome back to the Feynman technique. So today I'm going to be revisiting this integral. This is an integral that I've solved in two separate videos on this channel, both using the same method, but I haven't really been satisfied with the completeness of any of them. They're kind of hard to follow, and I don't really show a lot of what's going on. In this video, I'm still going to be skipping uh, some of the busy work. Anything that I skip is going to be stuff that people watching this channel could verify for themselves if they wanted to. Um, so there is going to be some stuff skipped in this, but I'm going to be as complete as I can with this. So you really get the idea of how to solve this using Feynman integration. All right. So, of course, our first step is going to be creating a function of t closely resembling our original integral. And this is an obvious reparameterization. We're just going to make it cosine tx over x to the fourth plus 1 dx. And we will note that f of 1 is going to give us back our original integral. Um, And f at 0, what's that? Well, that's going to give us the integral from 0 to infinity of 1 over x to the fourth plus 1, which is not a trivial integral to solve, but it can be solved using traditional techniques. Um, so I'm not going to show that, or else this video would be much too long. But that is something you can do on your own. There's plenty of videos on the internet on how to solve the integral from 0 to infinity of 1 over x to the fourth plus 1. It evaluates to square root of 2 pi over 4. Square root of 2 times pi over 4. That is the integral from 0 to infinity of 1 over x to the fourth plus 1. So our f evaluated at 0 is square root of 2 pi over 4. All right. Let's use the Leibniz rule for differentiation under the integral sign to find f prime of t. That's going to be negative integral 0 to infinity. And again, I'm taking the derivative with respect to t of f of t by taking the partial of the integrand with respect to t and leaving the rest of the integral alone. So this will be negative x sine tx over x to the fourth plus 1 dx. And we will note over here on the side that f prime evaluated at 0 is equal to 0, since sine of 0 evaluates to 0. All right, continuing, we're going to need to take some more derivatives, because eventually we're going to end up with a differential equation in t. So our f double prime of t is equal to negative integral, oops, let me draw a better integral sign there, negative integral 0 to infinity of x squared cosine tx over x to the fourth plus 1 dx. Now, this integral evaluated at t is equal to 0, f double prime at 0 would give us negative integral 0 to infinity of x squared over x to the fourth plus 1. And it can be shown fairly easily that the integral of 1 over x to the fourth plus 1 from 0 to infinity and the integral from 0 to infinity of x squared over x to the fourth plus 1 are equivalent. They evaluate to the same thing. So this would be negative of our whatever we got when we evaluated this at the point 0. So f double prime of 0 is equal to negative square root of 2 times pi over 4. draw a better 4 there. All right. Now we need to take yet another derivative. F triple prime of t is equal to, let's see, taking the derivative of our cosine would recover a negative sign, so we're going to have positive integral 0 to infinity of, now we have x cubed sine tx over x to the 4th plus 1 dx. And it might be tempting right now to assign the value 0 to f the triple prime at 0. It's actually not. The answer, it actually, at 0, as t approaches 0, this integral will approach pi over 2. And I will show you why that is. Because let's multiply the top and the bottom of this by x. So that means this becomes an x to the 4th. Now let's introduce a parentheses there and introduce a plus 1 inside our parentheses. But having added that plus 1, what we've actually done is added an integral from 0 to infinity of sine tx over x times x to the 4th plus 1 dx. So we need to subtract that. Like this. Okay. So now you see that this and this cancel. And as t approaches 0, for what's left of this integral, I've shown on this channel many times that value it's pi over 2. So if we let t approach 0, this whole integral evaluates to pi over 2. So I'm going to erase that and put pi over 2. Oops. How do I select things? I really ought to okay, well, whatever. We'll just leave it like that. And so now we can see that f triple prime evaluated at 0 is indeed going to give us pi over 2. All right. One more time. Negative integral 0 to infinity of sine tx. I can't have that big gap there. X to the 4th plus 1 dx. Now, let's get rid of this. All right. So now let's move on to f quadruple prime of t. And this will be the last time we have to do this. Well, taking the derivative with respect to t of pi over 2 is going to give us 0. So what we're going to be left with is negative integral 0 to infinity of, we'll recover an x when taking that derivative, which will cancel that x. So we're just going to have cosine tx over x to the 4th plus 1 dx. Well, you'll notice that is simply f of t. So now we have a differential equation in t that says f quadruple prime of t is equal to negative f of t. And that's a good thing. Because not only do we have that, but we have conditions here. We have f of 0, we have conditions for when t is equal to 0, which is the best kind of conditions to have. We really like to know specific values for t is equal to 0 in this sort of differential equation. That will make it much easier to solve. All right, well, to start, we have to find the general solution to this differential equation. And I'm going to kind of go through the thought process of how you might come up with this, even if you had never taken a course in differential equations. All right, so we want some function of t such that if you take 4 derivatives of it, you get the negative of itself. Well, it's probably going to be some form of exponential. So let's say e to the t. Okay, is that going to work? No, because you won't get the negative. All right, what about e to the negative t? Well, if you took 4 derivatives of that, let's see, you'd recover 1, 2, 3, 4 negative signs. So no, that's not going to work, because that would still be f quadruple prime of t equaling f of t. All right, so let's put some form of constant in front of that. Let's say, let's call it e to the negative a t. Well, what's going to happen if you take 4 derivatives of e to the negative at? Well, you're going to recover negative at 4 times. So if we took this and took 1, 2, 3, 4 derivatives of it, we'd get, let's see, our first derivative, we'd recover a negative a, and then our second derivative, we would recover another negative a, which would just be a squared. And then if we took another derivative, we'd get negative a cubed. And if we took one more derivative, we'd get positive a to the 4th. All right. So we would get a to the 4th e to the negative at, right? If we took 4 derivatives of that. Well, in order for 4 derivatives of this to be the negative of itself, we need a to the 4th equaling negative 1. And usually r is the parameter, the variable they use here. They call it generating a characteristic equation, I believe. But I wanted to show the thought process of how you could kind of intuitively arrive at the answer to this, even if you had not taken a course of differential equations. So we need our a to be such that a to the 4th is equal to negative 1. Okay. So we know our f of t is going to have this form. Our f of t is going to have the form e to the at such that a to the 4th is equal to negative 1. Okay. Well, this a to the 4th is going to have, by the fundamental theorem of algebra, I believe, is going to have 4 separate solutions. To figure those solutions out, let's convert negative 1 into its complex exponential. So negative 1 is famously equal to e to the I pi. Okay, that's going to give us values for a. Well, one of our values for a is going to be e to the I pi over 4. That's just by taking the 4th root on both sides. But that is not sufficient. We need to find the other 4. The other 3. The other 3 are going to be this, and you can verify this. It's going to be, that's e to the I pi over 4, not I pi over 4. That's important. Or it can also be e to the 3i pi over 4. It can also be e to the 5i pi over 4. And it can also be e to the, you guessed it, 7 I pi over 4. So those are our values for a. So the general form for our f of t is going to be this. F of t. Now we have to be careful here because we're using a lot of exponentials. It's e to the t times our a's. I'm sorry, oh, hold on 1 second. We also need to add a constant multiple in front of that. So our f of t is going to be a times e to the t times e to the I pi over 4. You can see this is going to get really nasty, which is why I'm going to be skipping some of the stuff that you can verify for yourself. So f of t is equal to a e to the t times e to the I pi over 4 plus b times e to the t times e to the 3I pi over 4 plus c times e to the t times e to the I pi. Let me keep the same format that I've been doing. We'll call that pi I. No. 5 I pi over 4 plus finally d times e to the t times 7 I pi over 4. Wow. Wow. Okay. Well, we got a lot more work to do. I'm going to pause the video right now and fill in f prime, f double prime, and f triple prime, and I'll get back to you when I'm done, and I'll show you what I did. Okay, so I decided to go with latex formatting here. Is it latex or LaTeX? I'm not sure. I think this will make it a little bit more clear, but like I said, we were taking, we found this to be the general form of our f of t. And if we take the first derivative, you can see that we'll recover the a times e to the t e to the I pi over 4 times the derivative with respect to t of t times e to the I pi over 4. So we'll just recover a constant multiple, or just we'll just of e to the I pi over 4. Likewise with this, all that happens is we multiply the thing by 3I pi over 4. For this one, it's 5I pi over 4. And for this one, it's 7 pi over 4. And then with each successive derivative, we get another of the same constant. So we'd add another I pi over 4 here, which is 2I pi over 4. This one would be 6I pi over 4. Adding 5 to 5 is 10I pi over 4, 14. And then on this one, you can see we have 3, 9, 15, and 21. So that's nice. So now we have 4 equations involving A, B, C, and D. And don't forget, we also have these boundary conditions. Don't forget we have these. So now we can make this a lot nicer because this looks horrible as it is. And I am going to pause the video again and put some more LaTeX up on the board. I'll be right back. All right, I'm back. And what I did was I evaluated each one of these functions at the point t is equal to 0. Okay, and then used what we already know. We know the following things. We know that f of 0 is square root of 2 times pi over 4. So I took our function f of t, evaluated at the point 0, and set it equal to pi square root of 2 over 4. And this is what you get. Because if you evaluate t at 0, all these exponentials just go away. So we're just left with f of 0 is equal to a plus c, a plus b plus c plus d, which is in turn equal to pi squared root of 2 over 4. Likewise, I did the same for f prime at 0, which we determined was 0. Again, these exponentials will drop out. These will not, because they're constants. They have no t's in them. But these will always drop out every single time. That's why it was so nice that we found values at t is equal to 0. But this is what you get. You get that you get the following equations. We get pi squared root of 2 over 4 is equal to a plus b plus c plus d. We get that 0 is equal to this mess right here, which I kind of simplified a little bit. I expressed it in terms of either so that the exponent was plus or minus I pi over 4 instead of having like all these, high value numbers here in front of our I pi. So these two things are equivalent, and you can verify that for yourself. It's not that difficult if you know a little bit about complex numbers. Likewise, f double prime of 0 we determined to be pi square root of 2 over 4. And that's in turn equal to this. And then these evaluate, all these e to the exponents right here, these exponents all evaluate to either plus or minus pi, and that's shown right here. So all these are equivalent. And then we have f triple prime of 0 equaling pi over 2, and that is equal to this once you simplify this. Okay, so where are we going from here? Well, we have the following system of equations, which I'm going to go ahead and paste down below here when I come back. Okay, so after having plugged in our t is equal to 0 into our functions up here, we got this. We got all this right here, which I simplified a little bit. So we are left with this system of equations. We have 4 unknowns, and we have four equations, making it absolutely possible, not easy, especially since we're dealing with complex numbers, but it makes it possible for us to find values for A, B, C, and D, which I've put over here. I'm not going to go through the entire process of solving for A, B, C, and D. There are multiple ways you can do it. You can brute force it by forcing one variable out, by combining them, by say like we could combine this with this, and this, each and every time forcing out one of the other one variable, and then we would keep doing that over and over again until we whittled it down to these values right here. You can be clever and match real and imaginary parts, and there's other tricks you can do. But whatever method you use, this is what you'll get. You'll get that A and D are both equal to 0, which is nice. That's going to simplify our equation a lot. And we get that B is equal to pi square root of 2 over 8 times 1 minus I. And that C is equal to pi square root of 2 over 8 times 1 plus I. Then if we plug in these values into our general form for f of t, recall that the general form for f of t was this right here. And if we plug in a is 0, if we plug in the values for a, b, c, and d, we will arrive at this. So this is our f of t. Now that's not a really good form for it, but technically that is f of t. And if we plugged in t is equal to 1, that would be the value of our integral. Now we can do better though. So we're going to do a little bit more work to kind of refine this equation a little bit. So to start, all we'll do is we will factor out a pi square root of 2 over 8 shown right here. Next, we converted this e to the negative I pi over 4 into its rectangular form, which is square root of 2 over 2 times 1 minus I. And all likewise, we did it with this one also. E to the I pi over 4 is equal to square root of 2 over 2 times 1 plus I. Next, we use the properties of exponents to split, hold on, to split this and this into two separate exponentials. So this e to the negative t squared root of 2 over 2 times 1 times e to the negative t squared root of 2 over 2 times negative I, and that's shown here. And we did the same thing over here. Again, nothing too complicated there. And next, you can see what we did is we rewrote this e to the I t squared root of 2 over 2 using Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. Our theta in this case is t squared root of 2 over 2. So that ends up being cosine of t squared root of 2 over 2 plus I sine t squared root of 2 over 2. And we did the exact same thing over here. Our theta in this case was negative t squared root of 2 over 2, but that negative inside here would go away because cosine is an even function. And the negative would distribute outside the sine function in the case of the sine function because it's odd. All right, let's scroll down a little bit here. Give us some more room. Okay, so this is what we get next, and that's actually going to be our final version of f of t. I don't see how to do better than that. And really quick, I want to show you how we made the big leap from here to here, and it just has to do with cancellations. Okay, so you'll notice that what do we really have going on here? We've got this pi square root of 2 over 8. That's not going to affect anything. Well, it'll be a constant multiple of whatever happens inside. So it's not going to affect it in any meaningful way. Um, so let's just figure out what's happening here. Well, let's see. We're going to have, let's see, 1 times cosine t squared of 2 over 2 plus a 1 cosine t squared root of 2 over 2. That's going to give us 2 cosine t squared root of 2 over 2. All right, what else are we going to have? We're going to have a minus I cosine of that thing, but then it's going to cancel with this plus I cosine, same thing. So that just, they go away. All right, what's next? We're going to have a 1 times I sine of this thing, but then we're going to have 1 times minus I sine of that thing. So that's going to cancel out again. So that's good. All right, and then we're going to have minus I squared, which is plus sine of this thing. And then we're also going to have minus I squared sine of that thing. So we're going to get 2 sine of that thing, which is t squared of 2 over 2. And then we're going to have, well, you could, it all cancels out. You can verify it for yourself that the cancellations will happen such that you end up with 2 factors of cosine t squared of 2 over 2 and 2 factors of sine t squared of 2 over 2. So we have basically a factor of 2 in here. We would have had a factor of 2 in here, which is the reason for that 4 being in the denominator there. So our final f of t is equal to this thing right here. So now it's very easy to find the value for I, which I think it's a really nice value for I. It's very strange. It's a form that you don't see come up very often, but here it is. And there you see it right there. Putting substituting 1 in for t, which we know from the very beginning of our process, back when I was actually writing things out on the board, we know that our function f evaluated at the point 1 gives us our original integral, which is this. So that's really cool because these are, you don't usually see cosine of, non-multiples of pi, or sine of non-multiples of pi show up as answers to integrals, but it did here. I thought that was really cool, and I hope you guys enjoyed this video. I hope it was a little easier to follow than the other two videos I posted showing me solving this integral. Um, but again, that's it. I hope you guys enjoyed that.